This video will explore user subjective evaluation of noise in correlation with objective measures using Altair Compose. The final judgment of comfort in response to vehicle noise is primarily based on the subjective assessment of each person, carried out through subjective tests. After evaluating the subjective rating of discomfort due to the noise, it's important to express this perception with an objective measure. The usual workflow takes vibration signals produced by simulation and tests using prototypes in order to compute objective parameters. Then, a group of specialists participate in subjective tests to assess how uncomfortable that vibration signal is. The next step is when a correlation is carried out between discomfort ratings and physical magnitudes of vibration. The first topic to be discussed is subjective evaluation. The assessment of how critical a noise is takes into account the distributions of critical bands in the human hearing. It is normally carried out by a group of specialists, namely drivers, that classify the different noises according to a subjective assessment scale. One example of subjective evaluation is the semantic differential method, which uses a survey or rating scale that classifies drivers' rate of the vehicle noise, such as this one that we see right here. Due to its simplicity and directness, it is widely used. Another subjective approach is paired comparison method, where we have a description of sounds in comparison to choose among them according to individual preference. In this table, we have an example for such method, where 3 vehicles were divided in 3 frequency ranges. The aim is to compare these 3 vehicles and choose which one has the highest amplitude of noise for each range. Some coefficients may be used to assess the agreement among raters. One of the most commonly used is Kendall's correlation coefficient, to determine the association between 2 variables measured in ranks. It is expressed by a ratio of variance of sum of ranks to maximum possible variance of sum of ranks, as shown in this equation, where m is the number of raters, in this case drivers, n is the number of items or classes to be ranked. The term di is related to the sum of ranks assigned to an item or class by m raters and to this ratio a. Spearman's correlation coefficient is another coefficient to determine the association between 2 variables measured in ranks. Between these two, Kendall correlation is preferred when there are small samples or some outliers, although it has a larger computational complexity compared with Spearman correlation. Our first example is how to use Kendall's coefficient to estimate the concordance of drivers' rates in subjective tests. We have a list of 10 people whose subjective evaluation originated the table that we just showed. The aim is to classify the loudest vehicle among A, B, and C options according to each frequency range. Each person ranked for each frequency range the lowest to the highest sound pressure amplitude. We can read this comma-delimited file with this function, and then we discard the headers, which are the first row of the variable. The next step is to save the data of each frequency range in a different variable. We also know that the number of items is equals to 3, corresponding to vehicles A, B, and C, and the number of raters, namely drivers, is the number of rows of our variable. With these 2 variables, we can calculate the denominator of Kendall's coefficient equation. Let's compute the terms to compose the numerator of the equation for each frequency range. Firstly, sum the rates given by the drivers, then sum ranks and divide by the number of items. With these 2, we can compute the term of the numerator whose squared sum will be multiplied by 12. With these values, we have Kendall's correlation coefficient. The same steps are done for the other frequency ranges. If we run the script, we have the results printed in the command window. The closest the value is to 1, the better the concordance among drivers is. With these results, we can see that they concur more in the second and third frequency ranges than in the first one, whose coefficient is smaller. Let's move to objective evaluation now. Since objective evaluation is susceptible to variability, especially for non-trained technical personnel due to differences among evaluators and variations for a single evaluator when rating the same noise in different periods of time, it's important to consider objective parameters in the assessment of user experience with noise and vibration. A weighting is the most commonly used frequency-dependent curve in various national standards, which is applied to sound pressure level microphone measurements to mimic the effect of human hearing. Given the same sound pressure levels, microphone recordings can be very different from the levels perceived by the human ear. It is employed by arithmetically adding a table of values to the measured sound pressure levels in dB. That means that the gain curves can be generated through transfer functions, as we're going to see shortly. As the ear is less sensitive to frequencies lower than 100 Hz, the A weighting gives less weight to that part of the acoustic energy spectrum, as we can see it in the plot. A weighting is mostly used to represent the sensitivity of the human ear as a function of the frequency for relatively quiet levels of sound, but there are other weighting curves according to the standard IEC 61672-1, such as B, which has fallen into disuse, C, mostly used for the measurement of peak sound pressure level in high frequencies, because we can see in the plot that it hardly provides attenuation in low frequencies, and D, for the measurement of high-level noise in aircrafts. Our second example in today's video is how to filter a signal using a weighting curve. Let's create a random signal whose sampling frequency is 41.1 kHz and sampling time of 0.1 second. With these parameters, we calculate the number of samples and can create the random signal and respective time and frequency vectors. First of all, let's calculate the weighting function according to this equation, so we can have a look at what the A weighting curve looks like. I will add a breakpoint here to run the script plot by plot. When we run it up to this point, we confirm that the A weighting curve provides an attenuation of sound pressure level higher for low frequencies than for high frequencies. The next step is to transform the signal from time to frequency domain using fast Fourier transform, whose result is double-sided. As most practical applications only use single-sided spectrum due to its symmetry, we can discard the second half of the FFT result. The numerator and the denominator of the transfer function are determined by this equation. Once they are calculated, we have the transfer function. These weights will be applied in frequency domain, and afterwards, let's recreate the double-sided spectrum before transforming the result back to time domain. Finally, this command creates the representation of filtered signal in the same shape, namely dimensions of the original one. Now we are ready to plot both the original and the filtered data sets. When we run the script, we see the second plot that has been generated with the original signal and the filtered one based on a weighting curve. Our last topic in today's video is correlation of objective and subjective evaluations. Before prototypes are put into production, many performance indicators are tested to judge if a vehicle achieves the design goals. Correlation analysis explores the relationship between each subjective evaluation and its corresponding objective evaluation to improve the reliability of the results. So, Pearson's correlation coefficient, it is a statistical index based on covariance whose value is between -1 and 1. It gives information about the magnitude of the correlation and the direction of the relationship, where value equals to -1 denotes a perfect inversely proportional relationship, and value equals to 1 denotes a perfect directly proportional relationship. This index can be expressed by this equation, where x and y are two random variables. It is the ratio of the covariance of these two variables to the multiplication of their standard deviations. And as it uses these statistical parameters of the variables, its meaning is more powerful than non-parametric coefficients, such as Kendall and Spearman that we just showed, because they use only the information about orders and scores of the variables. The next example covers how to correlate objective and subjective tests using Peirce's coefficient. Let's say that we have an objective evaluation with the energy of 3 vehicles in 3 different frequency ranges, like in the previous example, and the subjective evaluation considering which vehicle was the most uncomfortable with respect to noise. The two variables are expressed as percentages. Based on Peirce's coefficient equation, let's calculate the standard deviation of each variable. Then let's compute the covariance between them and compute the coefficient. The next step is to plot both percentage of energy, objective evaluation, and percentage who find each vehicle the most uncomfortable, subjective evaluation. Let's use a bar plot and add labels and legends. When we run the script, we see in the command window that Pearson's correlation coefficient is equal to 0.93, indicating a strong relationship between the subjective and the objective evaluations. And indeed, the plot reveals that the high energy in low frequencies, which usually generates the most uncomfortable noise for drivers, is strongly related with a negative subjective perception of drivers. Let's understand how the correlation led to this conclusion. What the first plot in area shows is the distribution of energy among different frequency ranges, which is our objective evaluation. For instance, for vehicle A, we have a higher percentage of energy in the frequency spectrum concentrated on the range between 50 and 80 Hz. On the other hand, for vehicle B, we have more energy concentrated on the range between 200 and 500 Hz. For vehicle C, on the range between 80 and 200 Hz. For the subjective evaluation, namely user perception, we see that more drivers consider the first frequency range of vehicle A as the most unpleasant among the 3 ranges. As low frequencies usually lead to a worse perception of vehicle noise, we have a higher percentage of dissatisfaction among users for vehicle A within this range. The same principle is applied for the other vehicles. Another correlation branch of methods is psychoacoustics, which is the study of the relationship between physical quantities of sound and subjective perceptions. In this field, various parameters may be calculated for this purpose, like loudness, subjective perception of sound pressure, standard ISO 532 regulated, for example, sharpness, a measure of the high-frequency content of a sound, and roughness, which is the subjective perception of rapid amplitude modulation of the sound, usually between 15 and 300 Hz. As these calculations are not trivial, they are out of the scope of this video, but Compose has all the bells and whistles to compute these parameters using its native math functions. A workflow can be built where the user passes a signal with pressure data and inputs the maximum frequency. Then Compose plots loudness according to the Bach scale, which is a psychoacoustical scale, and finally it calculates sharpness from the loudness values. Please visit Altair Forum, a place where users can interact, ask questions, exchange information, and post about model-based development.